Good morning, everyone. It's 10:10 here, so I'm going to get started. I know people are joining in and give a few seconds to join. We are in week 4, Wednesday, April 15, halfway in the month of April. I want to know what the weather is like where you are. So I want to start by a report from wherever you are. So I know James is up in the north in Washington. It's probably closer to Vancouver than it is to Seattle. Bellingham, he told me the place, he told me, and I never heard of it before.
Yeah, Bellingham.
He's from there, he grew up there, and I am curious to know what the weather is like. You'll take a look through your window and tell me what the weather is like where you are. Don't need to tell this place, but just tell me. The weather according to the class of CptS 317 today. In Pullman, where I am, when I look at the window, it looks cloudy. It was a nice sunny day yesterday, but it is cloudy today.
We got clear blue skies here in Bellingham.
Sorry?
We got clear blue skies here in Bellingham.
Okay, so don't make anybody jealous here. So okay, that's good for you. Is my audio on while you are there? Is it clear and good?
Yeah.
Okay.
Clear,
great.
warm.
Okay. All right, great. So keep telling me the weather. That's the very simple reporting you have to do today to just get warmed up. And I know people are joining. So warm-up question today is report the weather where you are. Take through a look through your window and tell us what it is like where you are. So I'm going to, while you do that, going to get started and start by having to, let me go to where I need to be. There is where I want to be. So I'm going to report. There is a good news today, and the good news is that homework 7 is out, and it is good for 3 reasons. Reason number 1, we have agreed, and I am going to keep my word that things will come in and go out on Fridays. Homework goes out on a Friday and gets submitted on a Friday also. Everybody knows it's not a Friday today, it's a Wednesday, but I wanted to release this one so you get 2 extra days. So the due date is not changed. It's a week from next Friday, April 24th, but it is out today and it is on Osbol. It got released at 9:30 for those of you who are curious and always check things there. It got out at 9:30 today. And so the good news is that you've got 48 extra hours to work on it. Reason number 1, that it is a good news. Reason number 2, I know some of you were really aching to get a homework. And so we've had the second midterm turned in and there wasn't much you would do. So you would hear me and we would have lectures and things like that, but you want to get into doing things. This course has got a lot of things that you would learn on your own. And some of you have already been telling us feedback to James and myself that you learn from this homework. They're clever ones, they're good questions, and so you learn from them. And for that reason, for those of you who are eager to see them, that's reason number 2. Why this is a great news. The third news is that it has got a problem that's about games, and I'm going to talk about that when I go through them. So there are these 3 reasons. 48 extra hours to work on it, a great chance for those who are very eager and aching to get a problem to work on, to get their hands dirty, and then because there is a game. Just like every other homework we have had so far, we will have 6 problems on this ones. And so there will be 6, but unlike some of the other ones, these ones have different weights. 4 of the problems have the same value, $20 each, 80, and then the last 2 problems have got 10 points each, and they add up to 100. And the problems that this homework deals with are on topics that we have done after spring break, after things are online. And more specifically, it will be on chapter 3 and chapter 4 of the book. Chapter 3 was on Turing machines, and chapter 4 was on decidability. So our homework 6 and the midterm had to do a little bit of things that happened before spring break. And the midterm had 1 question on decidability and a couple questions on Turing machines, but otherwise it was looking back. This homework is exclusively on things that we have done after spring break since week 1, according to our new calendar. And so Turing machines, chapter 3, decidability and understandability, chapter 4 is the subject of this homework. We are in the week we are in now, week 4, and we're dealing with chapter 5 of the book. We'll get to that in a second. And this problem is not focusing on that. The next one, the last one, homework 8, we'll take a look at what we are discussing this week. And so this one will only cover chapter 3 and chapter 4. So let's go through the problems. They are 6 in number. They are already on Osbol, and the submission is going to happen, of course, online. You will submit a PDF file, handwritten or produced. Both are fine, and if you do handwrite clearly, that's a reminder. And so the questions are divided in this way. The first problem is on Turing machines. It carries 20 points, and it is about having to show what Turing decidable language when they are closed under 3 operations. So there will be 3 separate cases, A, B, and C. A will tell you if I have a set of a collection of Turing decidable language, that set of collection of language is closed under concatenation, closed under star operation, closed under complementation. We've seen this when we were looking at things around regular language. You remember them, and so there were ways to prove them. And so the idea we have looked at things around proving something like this, not necessarily for operations and closure, is similar to where decidable problems were. So the basic notion there is, give me the Turing machine that does the job, that does this thing. That is what it means. In everything, and I'll walk you through these 6 problems. That's the goal of this slide. I will try to remind you what lectures cover these topics. Some of you are very good at following things, and you're taking notes, and you're following these lectures, and so you may not necessarily need to go back, but some of you may. And so these problems would make you go back. And I'll point to both the lectures where something that covered that topic happened and what section in the book are. And depending on how fast you want to get things, you could either look up in the book and read about it to solve that problem, or go back to the lectures. I think you will benefit doing both, and maybe the lectures would be faster in some ways to get to what you want to do, especially if you have missed it. If you have attended it, then you would exactly know where to go back, and so you don't need to look, maybe hear the whole thing, but you would go specifically to the place where it is needed. So problem number 1, 20 points, show that decidable languages are closed under operation, concatenation, and complementation. Problem number 2 is on one of the things we did in chapter 3. So we had 4 lectures on Turing machines. And so I think it was the second one on March 30th, the order doesn't matter, were a time when we introduced what the definition of a Turing machine is. And that was motivated by looking at Hilbert's tens problem. That's when we knew for the first time that there is such a thing called problem that is not decidable. And so the Hilbert's tens problem was, talking about whether a polynomial has got integral roots. And that was, we know now, and after having to prove things, that problem is undecidable. But the single variable version of it is decidable. And the reason for it is because we can design a Turing machine that would be bounded in the range it has to search for. And that one has got some limits on these things that are determined by coefficients of the polynomial and things like that. So I promised at the time when we went through that lecture to tell you that this ratio that will help us to say this problem is decidable is something I want you to prove it. There we go. So now we have the problem, and so there is a ratio and a range that will be satisfied, and it will be a little of math. So go back and try to be creative, but it is a math problem basically, and I would like you to solve that one. That carries 20 weights. That makes problem number 2. The lecture is on March 30th, and the book, the discussion of that that pertains to it is in section 3.3. We took care of 2 problems. Problem 3 has to do with showing a decidable language. And that language has got a name, and so it is on DFAs. And you probably have picked up from what we have discussed on the decidability and chapter 4, that we focused a portion of the chapter on talking about things that are decidable, and a portion of the chapter on things that are undecidable. The things that were decidable live in the world of DFAs and context-free grammars for the most part. And this one will take you to a place where you have a DFA and the language of A, when the DFA is A, when A is a DFA, is to say that all of the strings. So sigma star, and so all, in other words. And so that language is decidable. Go show me. The relevant lectures for it are lectures that happened on April 1st, April the Fool, and April 3rd. And the portion of the book that talks about it is section 4.1. Okay, we're done with the thing on the left. We've got the thing on the right. Problem number 4 is also from chapter 4. And when we transitioned into talking about problems that are undecidable, we did devise a tool that Cantor came up with, and that had to do with distinguishing between infinite sets that are countable and uncountable. So you will encounter one set that's uncountable in this problem, and it is very similar to an uncountable set that we have actually seen in the lecture, and that lecture happened on April 6th. And so you are asked now to show that concrete binary string of infinite sequence in some ways. You'll have a concrete description when you go to read the problem. You are going to take the diagonalization technique to prove it. And so it's going to mimic very much like what we did in that lecture. And so it will be worthwhile for you to look back that. If you have understood that, I don't think you'll have a big problem solving this particular problem. So section 4.2, a lecture on April 6th, and uncountable set, and the technique is diagonalization. That's the subject matter for problem 4. So that means we are done with the problems that weigh 20, and so now we have problems that weigh 10 each. Problem number 5 is on the very last section before we transitioned into what we are now doing. We looked at ATM was our subject. ATM, we wanted badly to show that it's undecidable. And so one of the things we learned along the way was this thing called, when you have a language, it's Turing recognizable and its complement is also Turing recognizable. Then when it is complement is, I shouldn't say also, when it is complement is Turing recognizable, that language is called co-Turing recognizable. So we talked about that, and we used this thing to actually, that's how we came to show ATM was undecidable. So here we are given a particular kind of operation that deals with co-Turing recognizable language, and you are going to show that this particular problem is separable when they are co-Turing recognizable. So you will see proper definitions for what that problem is. Okay, section 4.2, and the discussion for it was lecture that happened on April 8th. The last problem is where the game comes. This is the third reason why it's a happy day, that we are having good news, having homework 7 out, because it's got a game. That game is called Magic the Gathering. James told me that he grew up playing this game a lot. It's one of his favorites. And so this is going to make you take actually more like a collective view of everything that we've done in that decidability and undecidability chapter. So I had a hard time picking up which lecture to point to, but it is a fun problem, a fairly deep one that would make you reason around. And so there is a good description of what the game is. There is a result that is known about it that is fairly recent, and there's a literature on it. And so you've got a pointer to a paper in that problem, but there is a specific question you are asked, a question or two. And so you're going to answer, and you are going to answer by giving explanations for it. You don't need to write a whole lot. I'm expecting a few sentences, but well thought out. If you have understood the problem and the significance of the question, then I don't think the length of what you need to write will be a whole lot, but it will be something that will be a lot of fun to do. And so let me stop here and maybe ask warm-up question number 2. We did do serious stuff. We're going to work on these problems. We've got more than a week to do it. I'm not going to tolerate anything late. So April 24, the Friday midnight is what you have the deadline for. And so it's a fairly serious thing, but you've got a game at the end. So I have an opportunity to ask my warm-up question number 2 for the day. And that will be, so this we know is James's favorite game, Magic the Gathering. Maybe there are some of you for whom Magic the Gathering is your favorite game, but I want to know what your favorite game is. And so go ahead and tell me what your favorite game is, just like you have reported the weather. By game, I mean now card games, like whatever it is, like Monopoly or Magic the Gathering or any other thing. So go ahead and tell me. While you do that, if there is anybody who knows about Magic the Gathering, you could begin to think about what that problem that you are being asked now might want to tell you, but it is a difficult problem that people have come up with something that shows something cool with Turing machines is the story there. So this is a good transition point for me to get started with what we will continue with what we were doing last time. But please keep telling me what your favorite game is. And while you do that, I'm going to leave this slide open for a while so you see the nature of the problems and then what areas you will need to review to get to solve this homework. We are working on grading midterm 2, halfway through, and there is homework 6 that you haven't heard back. James is going to get back to that, but the midterm is going to take priority over homework 6. So there are 2 things in our hands. So you're getting this one, but we'll get a little bit of room in between them. And I think by Friday, at least midterm 2 should be graded. I don't want to report grades before we're done with everything. And so we'll wait until, well, that is done. And hopefully Friday you will hear. And that's James's and mine goal to get things finished by Friday, at least in terms of midterm 2. Homework 6 might take a little bit longer. We'll see how far that would go. Okay, so you see what these problems are. Maybe you will get a chance to look at the problems, and you've got a couple office hours now that we have actually releasing it, this one, including tomorrow's office hour James has on Thursdays. Will be a good time to ask questions to James if you need to set up a Zoom meeting during the office hour. The office hour is there. You don't have to set up, you use it. But if you want to have a quick question by email or something, you can still do that. But you've got more. That's one of the good things that it has been released. So you've got, instead of 2, you'll have 3 office hour options to ask questions once you get a chance to go through them. So it's unlikely that you will have a question at this point, but let me open up. You remember to unmute yourselves. If you have gotten a chance to go to Osborne and actually see what the problems are. Anybody has got a quick question on one of the problems or several of them before I get started with today's topic? Okay, so I don't necessarily expect you because you just heard, right? So you haven't even probably gone to Osborne to look at the problems, but look at them, and if you have questions, go get started. My advice will be get started as early as possible. There is competing needs, and I know there are many courses you take and things like that. And so having a little bit of a window, a longer window now to work on this one would help you. So you can have a couple problems solved on one day and another couple problems solved on another day. That would be a good strategy, but get started early and make sure that you have taken advantage of all the 8 homeworks you have available to submit so that you get your best 7 out of them. And so the 2 problem sets that are here, I expect everybody to participate in, even if you have done well in other ones. Don't leave out anything. Just take all 8 of them and work on them and submit the best solution you can have. All right, we're going to get started with today's discussion, and I'm going to back up a little bit and continue. And so that homework was actually a good point to show that there were things that were talking about decidability and undecidability. And that chapter finished by having to look at ATM, the acceptance problem, when the machine, when the model that we are working with is the Turing machine is undecidable. Everything else that we have with DFAs and context-free grammars, acceptance, emptiness, equivalence, they were all decidable problems, but ATM was not. That was what we did. And then we built up in the last lecture that we want to have more things undecidable because we know there are, and there is a method. And so unlike the ATM problem, which was fundamental and we had to do through the diagonalization method to show that it is undecidable, once we have that, we have a powerful technique to show more. Well, that powerful technique is reduction. So if I have a problem A and I reduce it to problem B, and if I know problem A was undecidable, then I would know that problem B is also undecidable, because if it were decidable, then I can go back and solve problem A, which I know is undecidable, and therefore there will be a contradiction. And so that general idea is called reducibility. So we spent a good portion of last lecture's discussion to make a case for that one, see in what other contexts it shows up. It's not just here, but other places also. And then we started looking at examples where we apply that by starting from ATM and reducing it to whatever it is that we want to show. And so we successfully showed 2 examples, the halting problem and the empty language problem on Turing machines. Both of them, we reduced them from ATM. And we started talking about a third example. And I told you then that it is okay if I don't get to finish it. So I'll pick up from it today, and we will we'll add a couple more examples. So this is something we had already started last time. And this particular language, we call it regular with all caps, and that is it's got a machine, a Turing machine. It takes an encoding of that one, and the language of the machine is that it is a regular language, and the result we have for it is that it is undecidable, and we proved this the same way we proved the first two examples, and we have gone through this proof idea. Where we stopped was the proof itself, but I want to very quickly remind you what the idea is. The idea generally for this one, for this problem, and generally for others also, is to come up with a Turing machine that will do the reduction, and we'll call that one an R, and we will reduce, we'll do that from ATM, and then we would construct another Turing machine S that decides ATM. That's the idea. And the idea for S, the Turing machine that would decide it, is to take this input, the encoding of the machine, and the string that we are reading, and to modify M so that the resulting TM would recognize a regular language if and only if M accepts it. This is where the place where it begins to take a special nature. Otherwise, the first statement is almost always the same for everything else that you would do. So in this particular case, because we're doing with a regular language, we're going to modify M so that it recognizes regular language if and only if the Turing machine is going to accept the input. And so we call that modified language M2. And we designed M2 to recognize a non-regular language. We picked a non-regular language by design, and we know it from our previous studies that 0 to the n, 1 to the n, when n is greater than or equal to 0, is a non-regular language. So we picked that one in the construction or in the design of M2, and we used that M to make it not accept W and to recognize the regular language, which is everything else, if M accepts W. So we talked about this step, and we then talked about how to specify S so that it can construct such a Turing machine called M2 and W. And we made M2 to automatically accept all strings that are in this regular language. That was part of the construction we have done. Automatically accept this, and if M accepts W now, M2 would accept all other strings. That's what the additional one was, and this is the place where I said I will pick up. And so you probably have noticed very carefully now, what I did was a little bit rushed, but it was intentional because we've gone through that last time. And this is the place where the formal proof would begin. And so when we stopped last time, if you remember, I didn't discuss this one, but with the recording ends with this slide. So from now on, everything that you would see will be new, but except for the story around homework 7, the rest of the slides that I went through now are some form. They're slightly different titles and things like that, but they were things that we have discussed. So the formal proof for this regular TM would be to put it in this way. So we are going to let the Turing machine that would reduce to decide regular TM, and then we'll go construct our S, and the S and the R here are terms that would kind of give you a hint for what they are doing. That one is, the R is doing the reduction and the S is doing the simulation. And so then S works in the following matter. So S on this input, which is an encoding of the Turing machine M and the input string W, it takes that as an input, and and it will have a few steps. So the first is to construct that modified Turing machine that we called M2. And so M2 will do its own thing. So it will take the input X, and if X has the form, this is where the automatic accept will happen. If X has the form 0 to the n, 1 to the n, which is a non-regular language, it will accept it automatically. If it does not, then M would run on input W and does what it does. And it will accept if M accepts W. So the first one is to automatically accept this non-regular language, and the second one is if it does not have this form, if it is a regular language, for example, then M would run this input and accept it if M accepts W. Then, now that we have this modified M2, we run R on this input, and then we would do what it does. We would accept. If R accepts it, we would accept. If R rejects it, we would reject. And therefore now we have proven that we can successfully reduce ATM into regular, because we know ATM is undecidable, and therefore regular TM is also undecidable. That's conclusion of an example we started last time. But this particular example has got an important additional things. And so those additional things, I want to comment on them now. So if you think about what we just did now is that we have, shown a reduction like we should, but there was a particular kind of property that a Turing recognizable language, when it is brought to a Turing machine, we were not able to decide. And we could use the same proof idea if regular was to be replaced by context-free language. So instead of saying, I've got a Turing machine and an input W, is this language now regular? If I replace that one, is this language now context-free? Is this language now decidable? Is this language now finite? All of these are undecidable. And we can prove them exact same way that we did. And somebody called Rice did notice this and kind of generalized it and said that the idea of having to determine any property of the language recognized by a Turing machine is itself undecidable. So now our list has really, really, really grown. So we had only ATM when we began last week, and now we have more and more examples. And so I'll add one more example. We'll add a couple more. But we'll go to example 4 now. And there is a little bit of a twist for what we will be doing now. And this twist is, first of all, let's first define what that example is, that language. And this one will take two machines, Turing machine M1 and Turing machine M2, and it's going to decide whether the language of the first Turing machine is the same as the language of the second Turing machine. In other words, equal. So the EQ there is for equivalence. And when we did this one for DFA, we knew we showed that was decidable, and we're not probably surprised now, but this one, when it is Turing machine, is undecidable. The reason this particular example is different from the 3 examples we have seen so far is in how we're going to use the reduction. So all 3 examples we have seen so far would start with our fundamental undecidable problem, ATM, which we have no other tool than diagonalization to show that it was undecidable. Once we have it, we use it to we reduce to another problem that we investigate. And by successfully showing that reduction, we say the new problem is now undecidable. But we've got one more fortunate thing for us to go to add to our tool. Just like we relieved ourselves from having to say, okay, every time somebody asks us whether something is undecidable, are we really going to go do diagonalization all the time? Or something equivalent to that one that will be hard labor from scratch to show that it is undecidable. We don't, because we have got reduction. And so we know we know one undecidable problem, and so we reduce it. And the one we knew was ATM, so we used it. We used example 1, we used it in example 2, we used it in example 3. But now that we've got this growing list, we could actually use one of these other ones also, because that one was undecidable because ATM was undecidable. So we might just as well use one of these undecidables also as a starting point for our reduction. And whatever else that we are going to investigate now, if we do show that this reduction is also possible, then the new problem will also be undecidable. So that adds to our toolkit. That becomes powerful. And sometimes some of these undecidable problems that we have shown by reducing from ATM may be a lot more convenient for us to use. This example is going to demonstrate that. So it's going to show equivalence between the two, but we have added some more. And so we're going to use one of them other than ATM to do the reduction. And that is going to be a reduction from the emptiness language, the ETM, which we know is undecidable. We've shown that in example 2, I think it was. Yes, halting problem, equivalence problem, the emptiness problem, regular, and now we are looking at the equivalence. So ETM was shown to be undecidable. So we're going to now show that if EQTM, the one that we are investigating now, were decidable, then the empty one would also be decidable. And so by reducing it from ETM to EQTM, we will show that this EQTM is undecidable. So the idea is actually very simple. ETM, the problem of determining whether the language of a Turing machine is empty, and EQTM, the problem of determining whether the language of the two are the same, have got something in common if I make, in this equivalence problem, one of the problems empty. So if I turn it around so that the equivalence problem would say one of the languages is empty, then the equivalence would mean that this other one that I'm trying to compare, if they're equivalent, would mean it's empty. So that means the emptiness problem is actually just a simple special case. So if one of these languages happens to be empty, we end up with the problem of determining whether this language of the other one is empty is exactly the ETM problem. So the ETM problem is a special case of the EQTM problem, and that is how close they are. And that's the idea we will use to reduce from ETM, the emptiness, to equivalence EQTM. And that is what I'll show you in this slide. As you can see, very nice, 2 steps only. So we let the Turing machine R that decides the equivalence, and we're going to construct an S that decides ETM. What do? S will take on input the encoding of M, and then it would have 2 steps. First, it will run R, the reduced one, on the input M and one of them, right? We have got 2 that we are going to show equivalence on, right? So it's going to take M and M1, where M1 is rejects all inputs. That means it's going to be empty. You see what is happening in the trick in number 1. So we took M1, and it is going to, this M1 is a Turing machine that rejects all inputs. If it does that, then it's empty. And so if R in the second stage now accepts, we would accept. If R rejects, we would reject. Why are we doing this? Because this first step would happen if it is empty. And so we have done the reduction of this equivalence to being something that we can show when one of the languages is empty. So if R decides EQTM, our reduction, then S, the one that we have now done for the simulation, would decide the emptiness language, because we just did the language that would be empty. So, but we know that ETM is undecidable, and therefore EQTM is also undecidable. If I were to ask you, I probably won't ask you to show this, that EQTM is undecidable by reducing it from ATM, you would have done, but it would have required a lot more steps. So this one is extremely simple, and that is to illustrate that we could use one of these languages that we have shown to be undecidable through reduction from ATM, could be used for reduction to show some more examples that are undecidable. Okay, that completes our tour of 4 examples of Turing machines that we show through reduction that they are undecidable. Hold to M, that was number 1. ETM, that was number 2. Regular TM, that was number 3. EQTM, which we just saw, was number 4. But then when we looked at regular, I told you Rice's theorem would tell us other ones also. So we've got CF, we never had this one. The ones that are written in blue, we never show them, but we kind of argued. That was one of the comment slides we had. And so now thankfully, we are kind of balancing this decidable and undecidable. Last time I told you, if we were tasked with going around like the forest and then say, here is a tree. Oh, is it decidable or undecidable? Here's another tree. Oh, is it decidable or undecidable? That forest, most likely the universe, I guess, I'm not sure, has got more decidable problems than undecidable problems. But the undecidable ones are not as few as you may imagine in the beginning. So we've seen all these Turing machine versions of the problems happen to be undecidable. So we've got a fairly long list of things. And this is what I wanted to get to as part of what we want to discuss today. We have a good, I don't know if it is a full 10 minutes, we've got some time. And so I'm going to continue discussing, but let me stop for a second and see if there is anybody who's got any questions from what we have been discussing so far. So I haven't followed up on the chat, and I'm sure you probably are commenting still on the favorite games part. Okay, so it should not distract you, by the way. So these warm-up questions are not replacements for the lecture. You know that, right? So that's probably what has been going on. But let me see if there is anybody who's got any questions on the undecidable things we've been doing through reduction. Homework 8 is going to have problems around this, so we should make sure that we are on board. Okay, so there are questions around, but so we can determine if a Turing machine is regular but not decidable. I'm not sure if I understood that question. Okay, I don't. So this by decidable here, I think I know what Harry's question is. What I have written as CFL and decidable here is let me actually back up and show you what I mean by that one. I think now I understand Harry's question. The comment part here. If we take a Turing machine and then to decide whether the language is context-free language, whether a language is decidable, whether a language is finite. This problem, they look a little cyclic. They are all undecidable. That's what the Rice's theorem would say, if that was Harry's question. But I think that's probably what it means. So I did not formally define what CFL TM is, what decidable TM is, but the idea for regular is extended there. That's the comment part, and that's what I'm trying to say with this part. All right, I'm going to now talk about another method or another additional method that we can use to use reductions for. And these are called reductions using computation history. For those of you who are really, really interested in Magic, the Gathering game, if you were to read that paper, you would probably see something that are really, complex and involved in formal ways of showing things and so on. I don't necessarily expect you to do that, but some of the things that is involved there would make you trace the computation history. And so we'll see a couple examples. We'll start today something, and we'll actually finish by showing something that is decidable, and next lecture will come up and see things that are undecidable. But there are problems for which the reductions would involve looking at computation history. So what is computation history? This idea is to use for showing that ATM is reducible to certain languages, especially when the languages are about having to show existence of something. This computation history, reductions that involve computation history will be useful. A good example for that will be Hilbert-Stein's problem. That was asking us for the existence of integral roots for a polynomial. So if we were to show something like this one, we're still using reductions and we're going to start from ATM, then we'll have to pay more attention in a way to how the computation is taking place when it is on a Turing machine. And that's what these reductions that involve computation histories would mean. So we will define this term, computation history, and show a decidable problem on it. And on Friday, we will show an example of a problem that's undecidable. Our task that we are very eager of doing is on the right hand. When we have these undecidable problems, we'll want to have more of them. And so we'll see a couple next lecture, but today we'll define what this computation history means and show a simple case where the problem is actually decidable. So it's going to be lengthy, and so I have chopped up things from the book, and so that I don't have to type too many things, but they will be easy. You remember when I talked about defining Turing machines in a formal way, there was this configurations, and so we would go from one configuration to another one. That what configuration means is, what the status of the tape is and where the head is and things like that. That's what the computation configuration is, and we'll go from one configuration to another configuration, much like what we do with NFAs and DFAs when we transition, and then we'll end up in an accepting configuration or in a rejecting configuration. So if we have a Turing machine M and an input string W, an accepting computation history for this machine, and this input is a sequence of configurations, and we can call them C1 through CL, where CL is C1 is the start configuration, and CL is an accepting configuration, and each of the CIs is legally follows from one of the previous ones. And then we will call that one an accepting computation history. Similarly, if the last state as CL happens to be a rejecting configuration, we'll call that one a rejecting computation history. Nothing but definition. Computation history means this. And we're going to define a special kind of Turing machine for the purpose of discussion we have now. And that special kind of Turing machine is called a linear bounded automaton. And so there's a formal definition there given, and it has to do basically to restricting the type of Turing machines we are going to work with in terms of what the tape's head is permitted to do. And so in this particular type of Turing machine, the tape head isn't permitted to move, is not permitted to move off the portion of the tape containing the input to the right. So we have learned about when we dealt with Turing machines, we saw ways in which we avoid having the Turing machine's head to go off the tape to the left. We devised some things to it, but we didn't say much about what happens on the right. In fact, we say the tape was infinite length. That was what it was. And now it is bounded. And then it is basically, we are putting a restriction on the memory of the Turing machine. So if the machine tries to move its head off the either end of the input, the head stays where it is. It's not going to move. And so the same way, the head will not move off to the left on the end of an input Turing's machine, a regular Turing machine. So that picture that you see on the slide is a good depiction of what a linear bounded automaton means. So look at the tape now, it is kind of finished, chopped off, and it is bounded. And so if we have an input, then our Turing machine would have only a linear multiplication of that input size as memory available instead of being unbounded. And so that type of Turing machine is called linear bounded automaton. So we are going to now define a language on this restricted type of Turing machine called LBA, linear bounded automaton. And so we've got a machine M, an input W, and LBA. ALBA is the acceptance version of ATM. Just like we have ATM now, we have ALBA. And this problem, I'll start with the theorem, is unlike the Turing machine version of it, the generalized version of it, decidable. The reason for it is because we have a way to see how many possibilities we have in this computation history, and so we can limit them. So what I have sandwiched between the definition of that language and the result we have is a proof, a step in the proof that we need, and this is a general enough technique that talks about what linear bounded automaton would do when M is a language like that. So if it has got Q states and it's got G symbols on the tape alphabet, then there is an exact number that we can put on how many distinct configurations we can think of for M. And that number is a product of three things. Q, which is how many states we have, N, the input size, and then we've got G to the power of N, and there is, the G is the symbols in the alphabet, and so we're going to have to allow all possible combinations is what it means, basically, very qualitatively speaking. And so this product of the three terms is going to give us the exact number of distinct configurations that could be allowed. And therefore, we will now know by tracing this history that we can decide because we have a finite size. Basically, that's what it is. I've got a couple of slides that talk about the proof for this lemma and the proof for this theorem. If we have enough time now, so I can tell you, but it was not too much of a thing that you need to be bothered about. The thing that I want to say is already said on this slide. So we've got defined a language that restricts the type of Turing machine we are looking at, and it has got linear bounded memory. And then so that language is now called ALBA. And we have a positive result on it that this is decidable, unlike its cousin when LBA is a general Turing machine. And the result for it follows from another general result that we can bring about by looking at how many different configurations, computation history configurations we can think of, and that number is bounded. Bounded by the size of the input, the length of the input, the tape of the length, and then how many symbols we have in the alphabet and how many states there are. And so here is the proof, just one slide on the lemma. That was the sandwiched part where we have got this Q, G to the N and the N, and here is an explanation for it. So we have a configuration of a machine is like a snapshot in the middle of the computation. That's what this, going from one configuration to another configuration to a third configuration until we get to the place where we have CL, which is the accepting configuration, or CL, the rejecting configuration. In which one of these, if we look at that and take a picture, and it will be a snapshot, that's what this configuration history would tell you. And this picture now that we took with our nice camera will have something that will be bounded, there are all the possibilities when they are considered, and that will be a product of those three things. That's what this proof in yellow box tells you, except that it is written in full sentences. All right. Because you'll have this slide, I'm not going to spend too much time on it, and so you will take a look back at it. Let me show you that theorem's proof, and then we will call it a day. Okay, so the proof of the theorem, which is a bigger one, that says we can decide this language, partly is done because now we know how much state is needed. And so our algorithm is now going to be an exhibition, just like we did for these undecidable results where we say We take problem A, we reduce it to problem B. Problem A was undecidable, and therefore B was undecidable. Just like that, when it is decidable, what we do is, here we have the Turing machine that does the decision for us. And we show that by exhibiting it. And so now our Turing machine that does prove the statement that ALBA is decidable, we will call it L, that Turing machine. And so it would take on input the encoding of the machine and the input string, and it will do two things. First step, it will simulate M on W for this many Lama-Taldas steps, or until it holds. Because the thing that we need to worry about in this decision problem, in the reason that ATM is undecidable, is because we never know whether the Turing machine is going to hold or not. It could loop forever, or it could get accept or reject. And so that looping forever is what we are trying to now say, that we will have a way to know it, because we would determine that it will loop forever if it enters one of these configurations more than once. And so there is a discussion that I have skipped. If you read in the book, you will know it. The reason that this proof would work is to say, now I have found a way to know when the machine is going to loop forever. It will loop forever if it happens to repeat one of these configurations in its computation history. And because I have now a limited number of them, I can see and then check if there is anything that has repeated. If it has repeated, then I would know the machine is going to loop forever. And so I have a way to know it. That's what this proof technique is. This proof is basically saying in words that are not written on that yellow box, but something that I have supplemented it with. This is the last slide I have. Next time, we're going to look at an example of a problem where we would look to see the computation history and to show that a particular problem is undecidable, which is the subject of chapter 5. And that reduction will be something we'll look at next time. All right, I have come to a good place to see if there is anybody who's got any questions. We've got a couple of minutes to see if there is any questions. Any questions? Was this all clear? All right, let me take a vote. This was clear. Say yes or no. You go to the participants. We've got 43 of us. And so I'd like to see how many yeses I would get. So what the lecture today, the discussion we've had today, was it clear? And be honest and say yes and no. And in fact, I wouldn't know who says no. So just feel free to say no. And it's not your problem. It's not clear. But let me see. Yes, I agree with William. It's clear, but you'll have time to lead. Yes, true. I agree with the comments. But just go ahead and vote. So clear, at least to the extent that you could follow in a 45 minutes or 50 minutes lecture. And so these sort of things are actually, would require more than one sitting, one reading, or one exposure. And so when you come back and look at this or read in the book, you'll be more familiar. This sort of things are not easy things that you would just follow along, understand, and then solve a problem. When homework 8 comes in, for example, it's not of that nature, but it is interesting, I hope, and something that you don't require too many repetitions either to understand. All right, there are many yeses, and keep saying yes if you agree. Yes. So I have to balance, right? So I'm not sure if I was extremely fast. I had a goal. My goal was to get to where we are now, and I had wanted to spend some time in the beginning talking about the homework 7. So I think those are fine. But I see enough yeses for people who are yes. Okay, we have a minute. Any comments? Sure. All right, so I think this will be a good place to stop. I will see you on Friday. Good luck with homework 7. Bother James, don't forget to nag him to ask questions, and I will see you all on Friday. Take care and stay safe.